Chapter number 10. In this chapter, our main focus is rotational objects. So we will talk about rotational variables, angular quantities. One of the important is actually we will talk about the rotation with angular acceleration, constant angular acceleration. Then we will take a look very in detail, rotational inertia. That's a really important concept when the large object do a rotation. And then we will take a look Newton's second law, rotational version, and also the torque and the rotational work done. Okay, let us start with the rotational variable. Let's consider I have an object starting at this point, and then after some time it will reach here. So we know the correlation between r theta s, magnitude of s should be equal r times theta. That's how defined the radians. Radian is equal s over r. Radian doesn't have any effect to the SI units because S is measured in meters, R is measured in meters, there's no SI unit. But how we define this in vectorially, right? That's important concept because all of these should be vectors. S has a direction, R has a direction, theta must have a direction. So let's consider this is red vector is the S vector, the black is the R vector right here on XY plane, and the theta is, we'll define upward direction on Z axis, okay? Theta is along K hat direction, R vector and vector is on XY plane, which means the both has I and j hat, okay, component of I and j hat, which mean I can redefine this vectorially. Vector S is equal cross product of vector theta and vector r. So the vector theta magnitude, vector r magnitude, sine angle between them 90 degrees, and then the unit vector S. Unit vector S represent the direction of the vector S that has component of I and j. So the magnitude, this is r theta S hat. The magnitude wise vector S is equal just r theta. Okay, so that's the idea, o theta r. So that's the idea, which means from here, if you redefine the magnitude of theta, that's going to be S over R. That definition of that angular quantity upward, which is important because that tells the rotational direction of any rotating object. Okay, now you can see rotational direction for this particular scenario is actually this word direction. Okay, so that rotational direction along XY plane is actually counterclockwise rotation. So this vector goes upward. On the other hand, if you redefine this to the opposite clockwise direction, vector should go downward. Okay, similar here, the angle theta is actually counterclockwise, that is XY plane. Then we know direction of theta is actually the Z hat direction, the K hat direction along the Z positive. Okay, so that's why we call that is positive theta upward. In case if this is moving downward, that we call negative. The reason why we call negative, now you can see the theta goes this direction. Negative theta means direction of that theta should be along that direction. Okay, that's the direction of theta, which is negative K hat direction. Okay, that holds what we define everything on chapter number 2. Okay, let's take a look. Let's take a look the idea of this rotational quantities a little bit in detail. Now, let's consider this is a disk, and then the disk is rotating on. Let's consider this is x-axis, this is y direction. Then this rotation is counterclockwise direction. So that we know this omega, we know it should be a positive direction. Why we know positive direction? Anything do counterclockwise rotation, try to bring the whole object along that third axis direction. Okay, then the omega hat, that is the unit vector for omega hat, which is equal to the K hat direction. Okay, now since the whole object is moving with omega, this whole object has the same angular velocity, but each radial direction velocities, each tangent direction velocities, and the radius is actually different for each point. Okay, let's consider this is point A, this is point B. Now let's take a look what are the correlation between the omega and these linear quantities. Okay, all right, so the omega is the angular velocity. Angular velocity is defined the rate of change of angular displacement. Okay, so this is going to be vectorially, I'm going to put omega hat there. So that is the direction of omega. We know in this particular case that should be k hat direction. Magnitude wise, we can just write omega is equal d theta over dt. Now, by using this, look how to get the idea of this relationship. So on the other hand, we know earlier is the linear displacement along the circumference, which is equal r theta. Then if I do ds over dt, that should be equal d over dt r theta. This you can apply the product rule. So this is going to be r times d theta over dt plus theta times dr over dt. Now ds over dt, which is how fast the object moving along the circumference, that is the tangent velocity v, right? So that should be equal r times d theta over dt, which is the omega. And on the other hand, per given point, r is a constant, right? So the per given point at point A, as the object rotating, r doesn't change. That's the main idea of the rotational motion. Because of that, this part should be remaining per given location. So we know v is equal r omega. We derive that formula another method in chapter 4b. You need to take a look at that method too. This is actually another easy method to take a look. And on the other hand, if you take a look now, these two, how these two actually arise, then we can find a correlation between the tangent velocities and the omega. Let's write it down for both cases, right? Point A, we can say V1 is equal R1 times the omega because omega remaining constant. And point B, we can write V2 is equal R2 times the omega, right? If I divide these two equations together, I can find the relationship between V1 to V2, which is R1 to R2. So if I rearrange this a little bit, we can say basically V2, which is equal R2 divided by R1 times V1. We know R2, which is much greater than R1. As a result of that, we can clearly say V2 definitely greater than V1, which means further away you go from the fixed point P, the tangent velocity getting larger and larger and larger because of the radius effect. But the omega for each case remaining the same. This point A rotating with omega, angular velocity, how many rotation per given time, and the point B does the same amount of angular velocity. Okay, so that's important concept. Let's take a look this direction again, little bit in detail. So all the directional quantities, remember we mentioned, should obey the right hand rule, right? If I put the x-axis and y-axis here, let's assume the object is doing this rotation, which means no counterclockwise rotation. So if you take your right hand rule and then curl your all four fingers towards the direction of rotation, then if you look at the thumb direction, that will tell you all the angular quantities. Okay, that is your k and direction. That's why we generally call counterclockwise rotation means positive theta. The reason now this theta along the k hat direction and everything else, okay? Omega also positive for this case because that's going to be along the positive k hat direction. If this is like, if you consider if this is like a screw, then the screw is starting to move that direction. That's the idea of this rotational quantity direction. Similarly, if you reverse the direction of rotation, now it is a clockwise rotation, x, y, z-axis comes out. If you apply the right hand rule, then we can clearly see the thumb direction is inward, that is the negative k hat direction. The clockwise rotation means our theta is negative. We know that theta negative means theta is in negative k hat direction. Omega also negative, which means negative k hat direction. That's the idea, which means we're going to take a look a lot of other angular variables, angular quantities in this chapter. All those angular quantities going to behave the same way. Okay? All right. So let's take a look a little bit in detail the angular velocity and the angular acceleration, because now in this chapter we are not interested uniform circular motion, which we discussed chapter number 4, which mean by keeping the angular velocity constant. Now angular velocity becomes a function of time. What happened? Angular velocity becomes a function of time. Now this is a function of time, which means it actually changes as a function of time. When this becomes a function of time, then I can find d omega over dt. D omega over dt is actually called the alpha. So on the other hand, we know omega, which is equal d theta over dt. So d over dt is going to be d theta over dt. The alpha also we can write, which is square theta over dt, square second derivative of the displacement. Okay. Now, if you take a look, the direction wise, wherever the omega and theta, alpha gonna be onto the same direction, right? So let's consider this is vector r direction, this is vector v direction. Then we know if the rotation is counterclockwise, that dotted line means the rotation is counterclockwise, then we know theta and omega both should be upward direction. Now, this is xy, the object is moving on xc plane. Okay? Now, in this chapter and rest of the chapter, semester, we can't really put always object moving on xy plane. You have to check very carefully what the direction of rotation, what's the plane of rotation. Okay, this is xz plane. As a result of that, you can see direction of theta and the direction of omega, direction of alpha. Everything is on positive j hat direction. Similarly, if I reverse the rotation, okay, so if I reverse the rotation into clockwise, then we know this is the tangent velocity v, this is the radial vector r. Then all our angular quantities now downward direction towards negative j, theta vector, and the unit vector or the direction of omega, and then the direction of alpha. All that small hat means a directional vector. Okay, all those directional vector pointed towards the same direction as positive j for the counterclockwise rotation, negative j for the clockwise rotation. If you apply the right hand rule, this behavior should obey the right hand rule too. Okay, so that's the important concept, which means generally we can say if the rotation is counterclockwise, usually all of these variables are positive. Okay, on the other hand, if the on the other hand, if this is reverse, then all the variables should be negative direction. Okay, but on the other hand, we can take a look. This another aspect. What is that? Is still we can say the rotation is counterclockwise, right? This is counterclockwise rotation. However, rotation rate itself can decrease. Okay, rotation is counterclockwise, which means rotation counterclockwise mean theta and omega direction is in this particular case j hat positive, but object can do deceleration, right? So deceleration means object slowly decreasing its velocity. Deceleration, if object doing the deceleration, we know alpha can be a negative number, which means alpha negative means itself going downward direction. Okay, so you remember the linear motion, the velocity can increase, then the acceleration towards the same direction as velocity can decrease, like the brake in the car, then the acceleration vector itself can reverse. Okay, this is such scenario. So this is still upward direction, but the alpha vector, which is the angular acceleration vector, can itself reverse its direction. Okay, depending on what happening in the system. So let's take a look a little bit more detail into our concept we built on previous chapters, particularly tangent velocity, centripetal acceleration, things like that. If you remember the chapter number 4, part B, we discussed there. We derive actually formula whenever the object is moving on the circular path, even if that object keep its angular velocity constant, which means only direction change, magnitude remaining constant on the tangent velocity. So even in such case, because of that directional change, it can provide a small change of velocity due to that motion. That small change always going to produce what we call the centripetal acceleration, acceleration towards the center. Okay. So the AC, we derive a formula which is equal R omega square, and we know V is equal R omega. If I rearrange these two equations, then I can find another relationship. So the AC is equal V square over R. We derive that equation on our chapter number 4B. You need to take a look there. That's an important derivation there. All right, and also we'll derive this, we'll write it down this vectorially too. We know now the rotational quantities on third direction, the third vector direction. Now this rotation, you can see rotation is on counterclockwise. If the rotation is counterclockwise, we know theta vector, omega vector, and the alpha vector all are on positive k hat direction, assuming this rotation is on xy plane. Okay, that's our drawing. Rotating on xy plane, then all the rotational quantities 90-degree angle to that rotation, right? So which means earlier we defined actually theta vector, right? So the magnitude, the direction, and the magnitude of the tangent displacement vector. So that is equal theta cross the vector r. So that actually we ended up just theta r and the direction of s, right? So similarly, I can redefine all of these other vectors, right? Which means the vector v, which is the tangent velocity vectorially, we can define vector omega cross the vector r. So that's going to be omega times r sine 90 is 1 direction of velocity v. That velocity v at any given moment has x component and y component. Okay, this v hat means it has more than one component. If you go back to chapter number 4 part b, we have all of those details there. Okay, which means similarly I can redefine another quantity. Now even the magnitude remaining constant, this velocity always, this acceleration always there, always present. Okay, but now we are not interested keeping that acceleration, keeping that tangent velocity constant. So we're going to let the velocity change, which means now we know angular acceleration percent, which means d omega over dt percent, or we can say d square theta over dt square percent. What does that mean? Angular velocity change. Angular velocity changes mean magnitude of tangent velocity also changes. All of these are changes, which mean dv over dt now present, right? So what does that mean? dv over dt present mean there should be acceleration towards the tangent. Okay, t is tangent, c is towards the center always. Okay, so that is present. So that present means now I have another acceleration at every single moment towards the tangent direction, which means we're going to have a two acceleration at all times, which means object will experience some sort of resultant acceleration that we can find a c square plus a t square root, and also we can find, which means some random direction. Okay, so this is, if I extend this line, this is going to be the AC direction, AT direction. So the resultant going to be somewhere there, which we don't know. A of r, we can find the magnitude by using Pythagoras. Angle relative to x-axis, relative to horizontal direction, going to be tan inverse y component over x component always, AT over AC. Okay, and all of those we can find very easily. And also we can take a look one other important parameter, this a of t. The vector of a of t we can redefine by using the angular vector alpha cross product the r vector, right? So which means the alpha r sine 90, and the direction of this gonna be tangent direction. I'm gonna put the unit vector at. Okay, and so on. All of these relationships are extremely important for the rest of the semester, okay? And then we will summarize all of these into one single nice format, which we exactly did on our chapter number 3 and 4, okay, by combining all the linear quantities together, right? So if you remember, if the linear acceleration remaining constant, then chapter number 3 we actually redefine everything. Like we know the linear velocity is equal dx over dy over t. Linear acceleration is equal dv over t. If acceleration remaining constant, or we can rewrite this d square x over dt square, then we redefine three linear equations, right? So the system of equation, what are the formulas are? Final velocity is equal initial velocity plus acceleration times the time. Displacement is equal initial velocity t plus acceleration over 2 t to the power 2. Final velocity square is equal initial velocity square plus 2 acceleration times the delta x. You can apply this directionally x, y, and z. So similarly now we can actually redefine for the rotational quantities. Let's consider rotational acceleration remaining constant, right? Alpha must remaining constant. Now we know omega, which is equal d theta over dt, and also we know alpha is equal d omega over dt, or we can rewrite that d square theta over dt, which means by looking into the correlation from linear to angular, we don't need to spend a lot of time on deriving. We can simply write by looking into the formula. You can even simply say we can easily take a look one formula here. If you take a look, this one d theta is equal omega times dt. Then if I integrate this one easily, we'll take a look this one here. So that is much be easier. So we'll take a look this one. So this is going to be d omega is equal alpha times dt. Let integrate both sides. Then the left hand side becomes omega final minus omega initial. Alpha remaining constant, this is going to be just t. So what we end up is actually this formula. Final angular velocity is equal initial angular velocity plus angular acceleration times the time. Now that formula is actually very good fit with this equation, right? Under one condition, which is acceleration remaining constant, right? Similarly, I can derive other two formulas very easily, okay? So which means we're going to end up another formula for the angular displacement, which is equal angular initial velocity times the time plus alpha over 2 times t to the power 2. Then the angular velocity final square is equal angular velocity initial square plus 2 angular acceleration times the delta t. Now, if angular acceleration remaining constant, I can solve the problem very, very easily by simply using this equation. Okay, so that's the idea. In this first part of this chapter, we will solving the problem under angular acceleration, but we are using simply these three equations, then we don't need to do the derivation or integral at all. Okay, so that's the idea. So let's take a look little bit in detail other important concepts. So one of the important concepts in this chapter is actually rotational kinetic energy. So the rotational kinetic energy means, let's consider I have a point particle. Let's start with the point object. So the point object, this is center point P, and then this is the radius R from here to here. The vector R direction. Let's assume we have object right here, mass M. Let's rotate this object along this path, which is the circumference, by keeping the radius fixed. So they need to rotate. Now the fixed axis rotation comes, that terms comes if you take a look. Now this fixed point, there is an axis passing through this point, right? So that is the z-axis. Now what this object does, it actually rotating around that axis. That is why generally we call this is a fixed axis rotation. One axis remaining fixed, object gonna rotate around that axis, okay? Now, if you take a look, the one single moment, let's consider object is right here. At that point, object tangent velocity is v, and object has angular velocity omega, right? So this is the tangent velocity direction, v of t, and then it has an angular velocity which is omega. So the angular velocity direction, since this is counterclockwise rotation, angular velocity direction is actually towards the k hat direction, right? So if I take a look this object mass m, and then what is the object kinetic energy at that particular moment? Okay, kinetic energy I can write mass over 2 tangent velocity to the power 2. That is that is a normal kinetic energy which we define on chapter number 7. Okay. Now that kinetic energy at any given moment must be there because object is moving. But object actually doesn't move on linear path. It try to stay here, but every time it actually drags towards the center, it's orbiting, right? So which means now we should be able to define some sort of rotational effect of this kinetic energy. That's what we're interested, right? Let's take a look how to get that. So we know V is equal R omega. Let's plug that back into here. Then I can find the kinetic energy simply gonna be equal mass over 2 R square omega square, right? Now, if you take a look, then the kinetic energy, I have all the rotational quantities now, right? Let's write the rotational kinetic energy, which is equal half m times r square times the omega square. This is a point particle. The particle mass is r distance away from the center. Now, if you take a look that all of these are angular terms, what matters is actually how the mass distribute around the center, not the mass itself. Now, this called the moment of inertia or the inertia effect when the object is rotating. Okay, when object is rotating, mass of the object doesn't matter. What matters is mass multiplied by radius to the power 2. So that I is called the moment of inertia, which is a very important terms for next few chapters. Okay, moment of inertia, we can redefine now kinetic energy rotational is equal half times I times omega squared. It is very similar to half me squared, but the linear moving object mass actually more effective. That is the inertia of the object. But the rotationally moving object inertia come not because of the mass, it is actually how the mass distribute around the center point. Okay, so that's the idea. So the point mass, we know moment of inertia is equal m times r square. This is for only point mass, okay? So the point mass, that definition is important. The unit wise, this is going to be kilogram meter square, okay? And now we'll take a look what happens if I have an extended object, because this chapter and next few chapters, we are not interested just moment of inertia or rotating of point masses. What we're really interested of how the object, large object, is actually does the rotation, what actually affect when the large object do this rotational motion. Then I have to take a look the extended object. When we're talking about extended object, then we can take a look one important parameter what we call the mass density. Usually we know the up to this point, if I have a three-dimensional object, we know it has a volume and then it has a certain amount of mass, like the sphere, cylinders, those kind of thing, 3D objects. Then we know the density of such object, we usually write letter rho. So these objects are three-dimensional, right? So the all three dimensions are important, which mean length, width, and height. All of these are measurable, and then very affected for the object shape and everything. Okay, so which means the density we usually write letter rho, which is usually mass or volume, and we know the unit is kilogram per meter cube. Now from here we can easily write the mass of this object, which is the density times the volume. If I consider a small, extremely small amount of mass here, which is dm, and then which mass has a dv of volume, inside that cube, then I can find the small mass is equal density times the small volume. The reason density doesn't care size or shape, that does care what the mass is, what this mass is made of, right? So the density remaining constant, but I can consider either large object or the small particle of that, which means every large object we can consider as a collection of particles, right? If I integrate this dm rho dv, then I'm going to end up total mass rho is constant and the total volume is v. That's the idea. Okay. Now, similarly, we can redefine this for other type of objects. Sometimes we can two sizes are two sides are much important. Very, very thin, like a disc, something like that. Then the length and width is important, but the thickness is actually almost negligible, right? Let's consider thickness of this object is extremely small relative to length and width. Then this is a two-dimensional system, right? Which means the area is what important. If I have amount of mass, that total mass is actually distributed over cross-section area A, then we define this density as a sigma. So the unit for this gonna be kilogram divided by meter square. Similarly, if I take a really small piece out of that, this gonna be small mass, small cross-section area A, is still the density gonna be equal dm divided by dA. Mass of a small particle, we can write sigma times dA. Okay. And then similarly, I can take a look the one-dimensional object, which means like the meter rulers, for example, which has a long length, but the thickness and the width is extremely small relative to the length. As a result of that, we can treat it as a 1D object. Then the total mass distributed over only length. As a result of that, we're going to say the density, we call the linear mass density, kilogram per meter, which is lambda. In this case, mass, we can easily write lambda times L. On the other hand, if you consider a small piece out of this, a small dm piece, length is dx, then we can say still the lambda must be equal small dm over small dx, small mass particle is equal lambda times dx. This definition is important to figure out some of the other important concept, particularly in this case, moment of inertia of the extended objects. Okay, that's why it is an important concept. Let's take a look how to get the moment of inertia of an extended object. Now, when we go into the extended object, let's start with the 1D object. That is much easier. So this is x-axis, this is y-axis. Let's consider this is the center of mass of the object. Then this axis y passing through the center of mass. Then the object total length is L relative to 0, 0 point. This is negative L by 2. This point is positive L by 2. Point A, point B. And then this is point P, which is the center of mass point. Now I want to find this moment of inertia of this object. Let's consider this object try to rotate around y-axis. Okay, if it's rotating around y-axis, then it will have a moment of inertia I. So that I gonna be axis passing through center of mass point. I want to figure out that. How to do this? So we don't know how to do the extended object. So what we're going to do, we're going to divide this object into small pieces. So let's consider each mass is dm, each distance is delta x. Then this look like actually point particle, right? So I have now the particle right here, which is dm mass dx, and the particle is orbiting around this axis y, right? So that particle is x distance away relative to the 0, 0 point p. Then the particle moment of inertia, let's consider I of particle is equal dm times x squared, right? Because it mass times r squared. That's how we define the moment of inertia. That is for a small particle. Now we can consider this object is collection of particles. So which means I can add all of these dm's together. Sum of I of dm together should be equal to the ICM of this particular rod, right? So which means I need to sum all dm x squared together. That summation we can do as an integral if object is nice geometric shape and if you know all the boundary condition for this object, which means I can basically say I of Cm for the object is equal integral dm x squared. This is going to be initial point to final point, but I have dm and x squared there. I can't do two variables there. You need to convert that two variable into one. That's why earlier we defined the idea called the mass density. So this has a mass amount of m distributed along L distance. So the mass density lambda, which is equal m over L. Now this has a small dm mass and a small length dx. That should be the same lambda, same density because it's the same material. It is part of the object. It's still the same density, right? From there, we can easily find the dm, which is equal lambda times the dx. Now I can rearrange this formula. Dm is lambda dx is squared. Lambda is a constant you can take out. This is going to be x squared times dx. This goes to x initial to x final. Now it is a single variable integral. I can just apply the power rule and then figure out the answer what we're looking into. Lambda remaining constant. Then I'm going to end up this going to be x cubed over 3, and then the limits goes from negative L by 2 to positive L by 2. Then if you apply the limits, I'm going to end up lambda, this is going to be L cubed over 3 minus minus plus L cubed over 3. So I'm going to end up then L cube of 3 we will take out. 2 to the power 3 is actually 8, right? So the L cube over 8, L cube over 8, I'm going to end up lambda over 3. It's going to be twice L cube divided by 8. This will cancel out to 4. So I'm ending up lambda L cube over 12. And on the other hand, we know lambda, which is equal M over L. If I plug that into here, this is going to be lambda is m over L, and then I have the number 12 here, and then L cube, this we can simplify into ml square divided by 12. That's an important equation. Why it is important? Moment of inertia always should be remaining look like that. Integral dm r squared. That cannot change. Okay, that's the fundamental definition for point particle. So that should hold, which means the unit wise we must get kilogram meter square. If you look at the final answer here, we're getting exactly that. What's the difference is that parameter 1 over 12, which means that parameter based on how the object shape look like. That's the idea here, which means next few chapters, when we're talking about large object, extended object, chapter number 10, 12, 10, 11, 12, and 15, we are treating the object with the large, its type and size matters. So as a result of that, all of these parameters will affect. Mainly moment of inertia is the parameter affecting first. Okay, so which means if I take a look all various type of shape of objects, now if I have a ring, then when the ring is oscillating, if I do that integral, I will end up mr squared. The unit should be remaining the same, but that number in front can differ, right? So it look like just a point particle because it's a ring, right? There's no mass distribution in between the r. But if I have a different object, like for example solid cylinder, then I will end up completely different answer, right? So that answer is still remaining the same, look like MR squared. What different is that front parameter. That parameter affected because of the geometry of the object. We know I of Cm should obey this sum of all I is small times the R square, or sum of all the I small for mass particle, which means sum of dm times the r square. So which means we can basically write I of Cm should obey integral dm r square. That r can be 1D, 2D, or 3D objects. Okay. So which means when I do that integral, this initial and final condition, depending on the shape of the object, I will get various parameter in front of that mr squared. Okay. So the MR score remaining always there, MR score or MD score, something like in the unit wise kilogram meter score, but you will get a parameter in front of that. That parameter is based on size and shape of the object. So that's why if you take a look, all of these different objects, this is a solid cylinder. Now this is a solid cylinder rotating in a different axis, and then this is a thin rod rotating its center of mass point and a different axis, and this is a solid sphere. This is a thin spherical shell. This is like a thin cylinder, and then this is a sheet, right? All of these, if you look at it carefully, it has a various different numbers in front of MR score. That's the point, okay? That number, because of the size and shape effect on that integral. Now, the main point is now, since you guys are in calculus class, how we get rid of this integral part. When we do problem, we're not going to do integral, right? So we're going to skip that integral part by doing this. All of these important equations are included in your equation sheet or the problem, which means the center of mass moment of inertia will be given. I of Cm for all of these different shapes will be given. But the problem when the object is oscillating, object is rotating, object can rotate by fixing various points. For example, let's consider this is the same rod, X and Y. We know center of mass is somewhere here, but now you can see center of mass axis is passing through there, but object has a different point fixed here. Let's consider point A, point B. Now, if I rotate this object around y-axis, then it rotating by fixing its endpoint, not the center of mass point. Then my equation, which actually given here, not going to be actually directly useful, because we know what happens center of mass moment of inertia if object is orbiting its own center of mass, axis passing through that point. But if the axis is different, I don't know how to do that. I have to do the integral again. Simply I have to redefine the integral for this part and then redo it again. Now we know I of Cm, we already figure out that that's going to be ml squared divided by 12. For this case, we interested I of A. To do the I of A, I have to do the same thing again. You can take a small dm piece here, and the dx length, and this going to be integral dm x square. This is x distance away from the fixed point. Then we can again apply the same concept. Dm is equal lambda times dx. This is going to be I of A is equal integral lambda comes out x times x square times the dx, right? But what is different here is actually initial and final condition. If you take a look, this is the initial point starting at x equals 0, final point x equal L. So this integral is now lambda 0 to L x square dx. Now, if I redo this whole integral, then I'm going to end up completely different number in front. I of A now, which is equal lambda, this is going to be x cubed over 3, and then the limits goes from 0 to L, right? So this going to end up lambda L cubed over 3, because 0 doesn't provide anything there. That part is 0. Then we know lambda is m over L. Then this is going to be L cube over 3. 1 L cancels out. The result is ml square divided by 3 now. So earlier, I got ml square divided by 12 if it's orbiting around center of mass point. Now, that's the important part. When we do problems, I can't really rely on ICM. Those are given in your table. But how are we going to figure out these results, what I needed for this problem? If I want to do that without the integral, what we're going to do, we're going to use the idea called parallel axis theorem. So parallel axis theorem is a shortcut to actually get rid of the integral, but figure out the moment of inertia around any other point other than the center of mass point. So what it says, I of any other point should be equal to I of center of mass of any given object plus mass of the object multiplied by h square. The h is actually separation between the center of mass axis and the new axis where it actually oscillating or rotating. Okay, so which means if I apply that concept here, I of Cm we know ml square divided by 12, mass of the rod, h is actually L divided by 2 to the power 2. Let's simplify this one little bit. This is going to be ml square divided by 12 plus ml square divided by 4. Let's simplify a little bit further. Ml square you can take out. This is going to be 1 over 12 plus 1 over 4. You can take the common denominator 12. This is going to be then 3 plus 1 is 4. ml square divided by 12. You simplify one step further, you will end up ml square divided by 3. Now, if you take a look carefully, the parallel axis theorem will actually provide a way to figure out this result, what I needed for new situation by only knowing center of mass, moment of inertia, and the separation between the two axes, center of mass axis and the new rotational axis. Okay, that's the idea. So which mean in our problem, the problem you do, actually you're going to apply the parallel axis theorem for most of the problem. Whenever it's needed, we're not going to do this integral part at all. We can get rid of that still, okay? Because the moment of inertia around center of mass will be given. So I need to figure out what is the answer, what I'm looking for, depending on the rotational axis where it is, okay? Now, that's the idea. You need to take a look. That's very in detail because that's one of the most important concept for most of the problem this chapter and also next few chapters also, because the object will not rotate only around its center of mass. When object does rotation, it can rotate any other point other than the center of mass point. Okay. All right. Let's take a look the last important concept on this chapter, which is the concept of torque. What's the idea of torque? Torque means the basically the idea of the rotational force, right? So let's take a look now. This is a door. So I can open the door by applying force, look like this, 90-degree angle to the radius. Okay, this is the fixed point now. You have to identify that's always. That point P is the fixed point and the fixed axis is the z-axis, right? So the along our the visual this is going to be xy plane. So I can push the object that way. Then this force is actually generating what we call the rotational force, right? Rotational effect to open the door. I can change the position where I apply the force. Then I can take a look again what that force, rotational force means, or I can maybe apply the force this not just 90-degree angle to the door, some theta degree angle to the door, right? So that is theta degree angle to the door. Still I can open, but my effect going to be changed. So the rotational force, which is torque, is equal the cross product between the R and the F. What does that mean? So that means it's going to be magnitude R, magnitude F, sine angle between them, and unit vector n. Okay, that unit vector n tells us the rotational vector direction, third vector direction. Okay, so these R and F vector usually on the same plane. Vector R and vector F usually on the same plane where those two are interacting each other. So the unit vector n we call the normal unit vector. What the normal unit vector means, the direction of the torque. Okay, real direction of rotational component is actually direction of the torque is 90-degree angle to the plane of R and F. In this case, R and F both are XY plane. Normal unit vector n should be k hat direction. Okay, so that's the idea. So on the other hand, if you take a look now, the torque can be affected by the magnitude of the R, how large the R is, how large the force is, how large the theta is, right? So which mean if I compare these two, in this case, let's assume force we remain keeping constant, right? If we keep the magnitude of the force remaining constant in those three scenarios, okay, which we have here, then I have torque for case 1, some magnitude, right? Torque for case 1 is equal R cos F. Take a look at case 1, magnitude of the R, magnitude of the F, angle between 90 sine 90 is 1, then unit vector in, right? So now that's the case 1. Let's consider this is case 1, this is case 2, this is case 3. Let's take a look at the case 2 then. Case 2 top of 2 is equal, that case R is now reduced, right? So the R is, let's consider R by 2, previous R by 2. Then it's going to be R over 2. Then magnitude of force remaining constant, it's still the sine 90, unit vector in. So this is going to be R if over 2. This looked like should be equal to torque for the case 1 magnitude divided by 2, for example, right? Unit vector in. Similarly, if I take a look the third case, torque of 3, which is equal R cross F, and then the magnitude of R remaining the same magnitude because it applied to the same place as earlier, and the magnitude of the F remaining the same, but now those two are some angle to each other. How to figure out the angle? You have to take a look always the direction of the R relative to the fixed point. Okay, that's the fixed point. Relative to the fixed point R, that is the direction of vector R, and then direction of vector F is actually that direction. So the total angle between the vector, total small angle between the vector, that's the angle theta we interested in this case. Okay, so that total angle, so it tells this angle is theta. If this angle is theta, this is 90 minus theta, which means this part should be 90 minus theta. So which means this total part gonna be 180 minus 90 plus theta, right? So this is gonna be basically 180 plus theta. We can figure out the angle accordingly. But what the point here is, this is affected by the angle, right? So this is gonna be basically sine of 180 plus theta because this angle is given as the theta, okay? Unit vector in, and then so on, right? So that's the idea, which means even if I apply the same force, the magnitude of the torque can be different depending on where I apply the force relative to the fixed point 2 and how I apply the force, whether it's a 90-degree angle to the radius or some other angle. That's the problem, okay? Now, on the other hand, I forgot to mention the unit of torque. If you look at the unit, that's going to be always meter Newton. If you write this to unit like Newton meter, you know the unit should be joule, but we never write the unit joule for torque unless we're talking about the rotational work done. We will take a look at that in a bit, okay? Generally, we write unit of meter Newton. Do not write unit of joule. That's not meaningful unless we're talking about the rotational work done, okay? All right, let's take a look this direction of the torque a little bit again. We know that should be 90-degree angle to the xy plane. We asked the linear component, linear vectors are acting. Let's consider, for example, if this is x-axis, this is y-axis, this should be the z-axis. Right hand rule should obey. If you take your right hand, put your all four fingers towards the first vector. Remember the torque we write this way. Whenever you write the cross product, what comes first actually matters, okay? This is your first vector, this is your second vector. We cannot reverse them. If you reverse them, yeah, the extra negative sign should appear, right? All four fingers toward the first vector, that's the first vector. Then you bend, curve all four fingers towards the second vector, right? Bending towards the second vector. Then you take a look, direction of your thumb. That direction tell you direction of the torque because it is actually R cross F, okay? If you take a look, torque should be goes upward direction if your curvature doing the counterclockwise rotation. And on the other hand, if you reverse it, then the torque direction will actually reverse, right? In this case, you can say this is the force F, this is the R, and then we try to move this object along this path. That path is counterclockwise rotation. If the rotation is counterclockwise, then we know torque is positive, okay? Torque is positive means if this is If this is x and y, now the plane of rotation is x plane. Rotation happening on xz plane as a result of that, direction of torque should be positive j hat. Okay. On the other hand, if I reverse the process, and then in this case, that is the force F, this is the radius vector R, this is the relative, the fixed point P. Now my rotation is clockwise. Clockwise rotation means I should know this is negative torque. The reason is still the rotation happening on xz plane. Since it is counterclockwise rotation, the result is actually negative direction j hat. Okay, so the torque should be downward direction in this case, torque should be upward direction in this case. Okay, so that's the idea. So that's how all these the angular quantities behave. Okay, and let's take a look one final important concept for this chapter, which is the rotational work done and the Newton's second law of rotational rotating object. So when the object is rotating, we know, let's assume we have object right here. This is the fixed point P. This is the radius R. The vector direction, I have a mass M. At any given moment, this object has tangent velocity. Let's apply the force into tangent direction, try to move it, but it's going to not move that direction because it moves in the circular path. It's going to move into that circle, right? But that given moment, object has that force set, which means I can basically say the force should be equal to mass times the acceleration. Force along tangent, what we're talking about here, the acceleration along the tangent, right? Now, if I do the R cross F, okay, R cross F both side, this side also R cross M times F. Now, if you take a look, the what we're trying to do here, so we are taking the cross product on both sides, then we know this side R cross F is equal R cross F equal to the torque acting on the object. When we try to rotate the object by apply the linear force, it will create the rotational version of the force. Okay, but on the other hand, this is a point particle. On the other hand, this side, I have R cross M of t. So let's simplify that a little bit. So we can rewrite this. R is 90-degree angle uh, to the tangent acceleration, right? This is the tangent acceleration direction. So we can write mass times magnitude of R, magnitude of A of t, and the cross product R to A t will provide the normal unit vector in. Normal unit vector in means the vector direction 90-degree angle to the rotational plane. Okay. Now, if you take a look at this equation, I have the torque is equal m times r a of t unit vector in. On the other hand, if you remember previously, if I have object has a tangent acceleration, which already have what we call the angular acceleration, right? Angular acceleration, I can always connect. Angular acceleration is the one always actually produce this tangent acceleration, right? So we can easily say tangent acceleration is equal r times angular acceleration, which means if I combine these two together, this becomes mr square times alpha unit vector n. This mr square, if you remember earlier, we defined for point particle, that is the moment of inertia. Torque acting on this particle is equal I times alpha unit vector n. This is the third version of Newton's second law. Okay, third version of Newton's second law. If you remember, we defined two versions earlier for linear moving object. This is the third version of Newton's second law. Now we're going to define another version later, then altogether the full version of Newton's second law we are applying in this class. Okay, so the torque is the rotational force, I is the moment of inertia, alpha is the angular acceleration, which means whenever the resultant torque is there, angular acceleration should be visible. Okay, And from this, we can actually easily define the rotational work done. Okay, so that's the plan. Let's assume object is started right here. We move the object delta theta amount relative to the starting point, right? So we apply a force and then move the object point A to point B, point A to point B along that circumference direction, right? So if I do that, then I can easily define the angular work done or the rotation. Okay, now let's take a look the work done. We can write the work done for this scenario, which is the dot product between the force and the displacement, right? So which mean in this case, force times the displacement, which is, let's consider delta S or ds. Okay, that delta S, this part right here, which is the amount it's traveling along this linear path, right? Because we know that definition, we try to use that to figure out what is the definition for the rotational work done, right? Now we know that delta S, we can write the cross product between theta and r, right? So the delta S vector, which is equal delta theta cross product the vector r, right? So because that how we define the direction of theta initially, very beginning of this chapter, right? Let's combine these two together. Now I have f dot product delta s is d theta cross product the r, right? Now we can rearrange this a little bit because I have a dot product and the cross product together, but we know linear component is only working with the linear terms, right? So which means we'll rearrange this a little bit. We can rewrite this by keeping the delta theta here, which is the dot product r cross F, r cross the force. Now this r cross the force is actually the torque, right? So basically we can rewrite the work done due to rotational effect is equal the dot product between the torque and the delta theta, right? So that's the idea. So we know torque and delta theta, usually if I rotate in counterclockwise direction, this is a counterclockwise rotation, then we know that particular rotation will produce all these parameters, theta, omega, alpha, and torque, all of these parameters on the same line, either upward or downward, either positive k or negative k direction. As a result of that, this delta, this dot product will actually produce torque delta theta. So that is the work done for the rotationally moving object. If I know what is the torque, net torque acting on the object, if I multiply by amount of rotational angle, I can get the work done. Now the important thing is the unit here. If you take a look, the unit torque has unit of meter Newton. Theta doesn't have any SI unit because theta is actually the basic definition of the radian. So the Newton meters now is actually the unit of joule. Only we put that unit if we're talking about rotational work done. Okay, that's the idea. I think that's enough all the theories. We will do problems in the class, so I'm going to stop from here.